Наш следующий докладчик Максим Татарченко из университета Фрайбурга. До этого он выпустился из МАТИ. Сейчас он в группе Томаса Брокса. Занимается синтезирующими глубокими нейронными сетями и представит свежие результаты. Слово Максиму.
Спасибо. I think I will give my talk in English. Hello everyone. I will talk about inferring 3D shapes of objects from single images of those objects using a convolutional network. And to motivate the task a bit, let's... Oops. Working. Okay. So, let's say you see a car image like this. This is a planar image, so you cannot use your 3D perception system to infer the 3D shape of this car. But because you've seen so many cars before and you know approximately what's the 3D structure of a normal, usual car, you can roughly imagine what this car looks like from different sides. So if you're asked to generate a side view of this car, you'd probably rather go for something like this than for something like this. And this 3D information is actually quite important for understanding and interpreting the visual world. So you can, say, seeing an image, try and approximate the interactions between objects, even when you don't see the actual 3D structure. So maybe it would be nice to learn such 3D representations automatically with our machine learning systems. And I will refer to this inner 3D knowledge, the 3D awareness. The question is, how can we teach our machine learning system to have such 3D awareness? And before I start answering this question, I want to first briefly introduce the concept of using neural networks for actually generating images, because most of the talk will be about generating images. Everyone is quite used at the moment already to classification networks. So we have an input image, we process it with a set of convolutional layers. There is a bunch of pooling steps in between which reduce the size of the feature maps. And in the end we have a bottleneck with fully connected layers. And finally we output the category to which the object or the image belongs. We can simply turn this upside down, and instead of having an image as an input, now have a category as an input, and generate an image based on that. So in the previous case, the main building block was convolution with pooling. In this case, the main building block will be up convolution. And it's nothing else than unpooling followed by convolution. So let's have a look. The standard pooling looks like this. This is our feature map. We have some spatial blocks, in this case 2 by 2, and in each block we take one element, or we compute a certain operation. This can be maximum, average, or like in this case simply taking the top left element, and then we build the downsampled feature map according to this row. Unpooling works the other way around, so we take a low resolution feature map, upsample each element so that it's now 2 by 2, and then, in this case, set this signal here to the top left element of the high resolution feature map. And then you can follow this by normal convolution. This whole operation is referred to as up convolution, and this allows us to build networks that generate images. And I will start by presenting some work by Alexei Vassilitsky, Tobias Springberg, and Thomas Brox from the University of Freiburg, which was about generating objects from their high-level descriptions. So in this case, with a cat image, it can be quite complicated to generate a realistically looking image because, well, obviously cats are quite hard. There are different kinds of structures and textures, but maybe we can first start with a simpler case and try to generate some easier objects in a controlled environment. For example, let's try and generate chairs from a set of high-level descriptions of those chairs. In this case, a high-level description would contain the style of the chair, in this case it's called this number 17, and the viewpoint. How the viewpoint is defined, we have a 3D model of a chair, and there is a camera moving around this model on a sphere. So the position of the camera is parameterized with 3 parameters, the distance from the center and the 2 angles, and we simply render this chair from a predefined position. Here is an example set of renderings, so there were not only chairs in this work, actually there was also an extension where cars and tables were added, and chairs were from this data set provided by Aubrey and colleagues. It was already pre-rendered. For the cars and tables, the ShapeNet data set was used. It's a large database of 3D objects, which we rendered using Blender. And yeah, this is the network architecture that was actually used for this task. So this here is the class label, basically the style of the chair or of some other object that we want to generate. This is the viewpoint we were talking about. And this is a set of transformation parameters which have the same effect basically as augmentation in normal classification networks. So they are there to prevent overfitting. These transformations are applied in the image space, so already on the rendered image. Each of those inputs is processed with fully connected layers separately. Then there is a bit of joint processing, and then there is this up-convolutional decoder, which outputs 2 images. One is the normal RGB image of the object that corresponds to these parameters, and the other one is a segmentation mask. For the loss in this RGB space, standard Euclidean error is used in the segmentation mask. So for the segmentation mask, it's negative log likelihood. And yeah, as I said, this work was originally done by Alexei Dasovitsky, Tobias Königberg, and Thomas Brox, published at CVPR in 2015. There was an extension as a journal version this year. We can have a look at the generations of such network. So the middle column is a bunch of chairs from the data set that this network generates. And of course, the simplest thing for the network to do would be to just learn several chairs by heart and output those. But this wouldn't be interesting, so this is not what's happening. And now let's start looking at the generalization capability of this network. So the first generalization is actually over transformations. During training, all the transformations were sampled randomly from some set of from some ranges, and of course the network hasn't seen each particular transformation value for each particular object. But in this case, you can see that we can traverse the manifolds of each transformation, and it generates consistent chairs, so it really applies those transformations in a reasonable way. Another generalization is across styles. So the network can only work with objects that it has seen during training, but what we can do is we can not simply take one object over another one, but try and smoothly interpolate between those. So we can take the input vectors corresponding to this chair, to this chair, the input vector corresponding to this chair, then compute an interpolation between those vectors and decode. What we get looks like this. So the network actually has learned some reasonable chair manifold, and every image in the output is chair-like. The same, of course, works for other object types, in this case cars. One can even train a network on 2 classes simultaneously, for example, chairs and tables, and interpolate between a chair and a table. And of course, in this case, the task is somewhat more difficult because the gap between those 2 classes is larger, but the network still figures that, well, there should be something in between that looks like this. And another funny experiment one can do with this setting is hidden space arithmetic. So the representation that the network learns is supposed to capture some kind of high-level concept. And we can try and play with this high-level concept, perform some simple mathematical operations on the hidden vectors of the network. I'm not sure, I think in this case it was the second, so features computed by the second fully connected layer. So we can take, I think this second row is especially nice. We can take this armchair with armrests and rolling legs, subtract this chair, which has the same type of back, and add this one, which has a different type of back. And then what we get is a very similar chair, but with a different type of back, so this one. So we can kind of subtract and add concepts that result in reasonable images in the image space. Okay, and finally, the next type of generalization that this network has is generalization across viewpoints. So during training, the network has only seen a fixed set of viewpoints, but of course at test time we can also sample something in between, and it will result in, again, reasonable images. But one can take this one step further, and for certain models from the training set, in this case for 10% of the models, not show every possible viewpoint at training time, but rather show only some fraction of it. For example, here we will only use 15 azimuth angles out of 31 available in total for this 10% of chance. But at test time, we can still request to generate all possible viewpoints. And the network will need to do something called transfer learning, so to learn, to transfer the knowledge it has learned on some other task, on some other objects onto those objects. The results look like this. It can interpolate the rotation even though it hasn't seen certain angles for this particular chair. And of course the quality of the result depends on the number of viewpoints available during training. The less, the worse. And in the most extreme case, when we only show one viewpoint per object, it can be seen, in fact, as a problem of novel view reconstruction. So we take one image that is shown to the network, and then at test time it has to generate all other images of this object.
Can you go one step before?
Yeah.
I just feel that I cannot see a difference between 4 images in the middle.
Between, you mean here?
Like 4 or 5 times.
Between these two?
I don't see the
Wow. The rotation is not so large.
Yeah, but on the next slide I see the reach. Not here. I mean, with the chip, it's obvious.
Yeah, I'm not sure actually if the angles are in exact correspondence in this
The very
case.
slight one.
Well, okay, for the top row.
So also here they are not in exact correspondence, right?
Where do you point to?
So here in the first column.
Yes, I understand, but I'm looking at the row. And I see, let's say, the first 3 examples they are taking, and then the second 3 pictures are quite similar. But the gap between 2 pictures should be the same angle, right? I mean, the step in terms of angle is the same.
Well, no, for this armchair, it has to rotate it in the end by 360 degrees.
Within 1 row.
Yeah, well,
Okay.
yes, within 1 row, yes. I mean, it maybe has slight deviations in terms of the angle estimation.
I just want to comment that this example doesn't show that it's learned to interpolate, because it looks like it just goes through one example.
Okay, maybe wait a moment and we'll go to another example where it will be obvious that it actually learned to interpolate. So this is an image, we'll have a video later. So If we want to, the problem with this approach is that if we want to actually do this null view reconstruction, then we need to add one image of the object we're interested in during training and fine-tune our network with that. So it requires retraining for every new image, which is bad, but we can change that and add an inference part to this network, which will allow to do the same thing, but for objects that were not seen during training. And this would look like this. So the green part is the decoder, which is more or less the same as before. And the blue part is now the encoder that takes an input image of a certain object, processes it, computes some hidden representation, modifies this hidden representation according to the transformation that is also given as an input. And in this case, this transformation is simply the viewpoint transformation, so it's the desired output viewpoint of the object, and then it's decoded into another image. This is the work that was published at ECCV this year. And yeah, as I said, now we can work with objects that were not seen during training at all. Example is here. We have two objects, and the network can generate novel views of those objects that look like this. The top car is what we call a normal car, so it's a simpler case. The bottom one is more difficult, so you can see that the results for the bottom one are somewhat blurrier, but still the network learns to somehow estimate the shape and the color and also the viewpoint of the object. Okay, and here are some more examples. Actually, I hope this would answer your question now. That the network, in fact, can interpolate between the viewpoints. And this is what I wanted to point out, that this is just an animation that was compiled from images, single images generated by the network. So in this case, you can already see that those animations look like 3D models, although there was no consistency enforced between different output views. But we'll make this more explicit in a moment. Okay, one can make another step, and instead of training on images that have some homogeneous background, also learn to segment objects from the background. Since we're using synthetic data, what we can do is we can simply place each rendering on top of some random background image. In this case, we took images from ImageNet, and use these as training data. And the network can, in this case, generate predictions like this, which is not very surprising by itself. So again, we can have a look at this video, and again it works. But what's nice about it is that one can take this network trained on synthetic data and without any modifications, without any transfer learning, apply it to the real world pictures. This is shown here. We take a bunch of real cars. There was no pre-processing involved, so I only cropped those cars to match the input size of the input image size of the network. And yeah, each car is centered. The scale may actually differ. And this is what the network reconstructs. So it has indeed learned to somehow infer the shape of the object, the colors. Of course, the reconstruction quality is somewhat less than before, because the problem is also harder, but the network does a reasonable job. One important thing is that in order to make this work, you need to be very careful during rendering. So if you simply render an object, put it on top of the random background, and use this as training data, it won't work. Because there will be a sharp transition between the foreground and the background. The network will quite simply learn to overfit to this for segmentation, and will then fail completely on the real world data. So what we used in the paper, what was also shown before in the paper called Render for CNN, that you need to randomize everything. You can randomize the number of light sources and the positions of light sources and their intensities, and the blending between the foreground and background, and the overall smoothing of the image. And if you do this, you can get such results. Okay, and now how can one make the 3D representation explicit and get an actual 3D model of an object? So this is our input image, and since we're using synthetic data, again, we can without any effort, additionally generate depth maps for each of the training images. And we can also predict those depth maps with a network, just as an additional output channel. Then we can take one input image, generate multiple output views with the corresponding depth maps for it, and fuse those depth maps into a single point cloud. We get results like this. So on top is the actual raw point cloud that one gets without post-processing. The bottom image is this point cloud when optimized using some variational algorithm. So in this case, it's converted into a mesh. And here are some more results of this. Here I want to emphasize two things. First, that I've already mentioned before, that the network has never been enforced to generate consistent results. So it always generates single images, and it has learned by itself that different output views of the same input object should be somehow consistent. Second, this whole setup is different from the structure from motion, for example, that we've seen before, or from depth from single image reconstruction, because in those tasks you estimate something for the pixel values that you see in the image. So for example, you estimate depth for some pixels that are seen within the image. In this system, we learn somehow prior shapes and estimate data that is completely missing in the input image. So the network hallucinates parts of objects that are not seen at all. Here I would like to give a brief overview of the related work. There were a couple of other papers where people solved similar or almost the same problem. One is this inverse graphics networks, IGN by Kulkarni and colleagues, which was published at NIPS last year. And there they used the variational autoencoder with a disentangled hidden space. So they separated the hidden space of their network into several parts, one corresponding to this explicit rotation, the other one, I think, to lighting, and the rest to all the rest, to the appearance of the chair or of the object. And they get results like this. Top row is in each pair of chairs is their result, bottom row is ours. Unfortunately, we couldn't use exactly the same chairs as they did, but we picked some similar models. And you can see that in the top row, which is claimed to be a positive case, the rotation is estimated quite poorly for those viewpoints which are different from the input. And for those other two cases, it actually fails completely. Whereas our network generates, well, consistent results everywhere. This is the direct comparison to the previous work I was talking about, where we can add one image into the network for generating chairs, where we can add one image of an object, train with it, and then generate all the missing viewpoints. Again, no, not again, just top row is our rendering from this work, bottom row is rendering from the previous work. And you can see that actually both perform quite well. The only problem is that the previous work, which can be seen in this bottom chair here, overfits somewhat more. So when the output viewpoint corresponds exactly to the input viewpoint, the rendering is more or less perfect. However, when we deviate more, you can see that the chair model changes, and this is a signal that the network overfits and simply generates something from the data set. And another work is a recurrent network by Jimmy Young and colleagues, also from NIPS last year, where they parameterize their rotation as some fixed operation. So they say that they always perform rotation by a certain amount, for example 15 degrees in this case, and then they apply this rotation recurrently. So to get this row, they would need to input this image and then recurrently apply this rotation and generate every next image. And again, you can see that their results, which is the top row, is much more blurry than those in the bottom row. Another problem with this approach is that you cannot, if you want to have some smaller angles, then you will need to apply this rotation more times, because it's a recurrent network. And this can result in error accumulation, which is also not desired. Finally, the work from ECCV this year, which I find very cool. It's from Berkeley, and what they did, they also generated novel views of objects, but instead of predicting raw pixel values, as we do, they predict something they call appearance flow, which is simply a permutation of the input pixels, which is needed to be applied in order to compute the output image. And as you can see, it works really well. So it can generate some fine details, which we miss. But it also has a number of limitations, so it's very good if the output viewpoint is quite close to the input viewpoint, so if the input contains all the information necessary to generate this output. But of course, if you have, for example, orthogonal views, it will fail completely because you just won't know what to do. You won't have the desired color palette. And also, from their work, it's maybe a bit harder to make those 3D models explicit. So we also don't concentrate on this. Okay, and now a couple of more experiments to show how the network performs. First, I would like to show how the network uses information from the input image. Let's say it gets a car image like this, then it can generate predictions that look like this, and they are quite fine and consistent with the input, but do not necessarily correspond to the ground truth. You can see that the car body type is different. This is because this information is simply not present in the input, but what is nice is that as soon as this information becomes clearer, the network actually learns to use this information, and once we can see the model exactly in the input, the output also corresponds to the ground truth. Again, we can do the same type of interpolation, now not in the input space, not in the input parameters of the network, but in the hidden space that is done by the network. So we can take two cars, compute the hidden vectors using the encoder for both of them, and then smoothly interpolate between those two, decode, and we get results like this. So the manifold that the network learns is also continuous and traversal. And finally, the property we would like to have is that if the car model, or just an object model, is clear from the input image, then different viewpoints of the same object should lead to the same hidden representation learned by the network. We can verify this in the setting. We take multiple cars, each from several different viewpoints, where each viewpoint displays the model. Then we run them through the encoder, compute those hidden vectors, and build the matrix of pairwise distances. What you can see is that there is this, well, not perfect, but obvious block diagonal structure, which exactly corresponds to this effect, that hidden representations for different viewpoints of the same car are much closer to each other than those of different cars. Actually, the most obvious confusion is this element here, which corresponds to confusion between this car number 2 and the car number 5. You can actually see that their shape is also somewhat similar. This shape is the most important clue for the network. Okay, to sum it up, I've shown that it is possible to generate high-resolution images of objects with a convolutional network from a set of high-level descriptions of those objects, and that the network does not merely learn the objects by part, but it actually learns some meaningful continuous manifolds that can be traversed, and then we can enhance this network and add an encoder to this, which allows to infer 3D representations of objects from their single images, and that finally this internal 3D representation can be made explicit by predicting depth maps and fusing those depth maps from multiple output viewpoints into a single point cloud. And that's it from my side. Thank you for your attention. Also, the code for both works is available. You can download it online. Thank you.
Question. So at some point, some of the interpolated views were lacking sharpness a bit. Do you have any intuition whether you could add some sharpness constraint or thermal sharpness?
Yeah. So from what I've seen, what I've observed, all the views actually are equally blurred. And the reason for this is, well, there are maybe multiple reasons. Probably the main reason is that we simply use Euclidean laws, and it favors average shape somehow. It would be nice to also learn some details and kind of, you can see it as having a multi-modal distribution in those possible outputs, and we would rather like to stick to one mode and not predict something average, which the Euclidean laws actually does. We tried using GANs for that, actually combining GANs with the Euclidean laws, and it worked somehow. The results look sharper, but not necessarily better, so it's rather they get more noisy. Yeah, one could try some other loss types, for example, perceptual similarity loss that Alexei will talk about later today. There are ways, but we didn't really try to improve that a lot. Yes.
Thank you for your brilliant presentation. At some point you have shown that the new approach has a better, does overfit less than the previous approach. Could you please highlight what steps taken contribute to that most?
It's maybe a bit hard to say exactly what leads to this behavior because we didn't perform any extensive study on that. But one huge difference, I think, is that in the previous work, the light sources were fixed and only a fixed set of renderings for the.
So that extensive randomization you would refer to.
So in the previous work, there was less randomization.
Yeah.
There was some randomization of the transformation parameters in the output space, so in the image space, but the rendering parameters were not randomized. And in this work, in the late work, we used a real-time renderer, so we didn't actually pre-render a set of images, but we rather generated them on the fly. So the network has probably seen more views with more variation, and maybe this was one of the reasons for better generalization.
Yeah.
On that slide with element subjects and images, objects, are they really often, good examples, or is there a
So, okay, maybe we don't actually need this slide. So the question was if this arithmetic in the hidden space, if those examples are cherry-picked kind of, or if this is really general behavior. And I'm afraid I cannot answer to this question based myself because I didn't perform those experiments, but the author is here, and maybe we can ask him if he's here. Well, maybe he's not. Okay, but maybe we can answer this question later.
The slide with the videos are partially answered, where the cards are interpolated.
Oh, well, those experiments were performed in the previous paper, so in the chairs paper, and the videos are from the later papers.
In the chairs paper, had all the range of results from good to bad, and the bad ones are not that bad. That was the question.
Can I ask, is it fair to say that your model inside of it has implicit probability distribution that takes into account the shape of an object and the texture on it?
Yes, I mean, it is some kind of joint representation of shape and texture. Actually, maybe we can have a look at the network architecture once again. So you can see here, this representation is exactly this type of information you are asking about. So this is the representation of the input object without adding the transformation. And I like to see it this way, that first this representation is inferred from the input image, then we compute this transformation, then we here transform this representation according to this transformation, so kind of implicitly rotate the object, and then this part is, so to say, the renderer that decodes it into image. It's probably not exactly what's happening, but it's maybe some intuition.
Do you think, is there a way maybe to make it more explicit, to give it just shapes without colors, it's even filled, or have some textures, and see what kind of shapes those textures should be on?
Well, I'm pretty sure there is a way one can try and learn the disentangled representation. What exactly way to use for this, I'm not sure. So one possible way is the related work I've shown with variational autoencoders where they train this disentangled representation. There are also other possibilities, yes. I think it's possible, and we didn't try that.
So, to show that your method works, you always show images. Is there a meaningful way to do some quantitative comparison between methods?
Yeah, thank you for this question. We also did some quantitative comparison. We compared it to the baselines. The baselines are very simple. It's just nearest neighbor in some space. So instead of generating images as we do, we take the nearest neighbor from the data set according to some metric. The problem is that those numerical evaluations are not always meaningful, because for a numerical evaluation you can also only consider something like L2 loss, and the L2 loss is not a very good comparison. But what is... Yeah, well, yes, I think that's the answer.
Okay, maybe the last question. Can you say more about the convolution step? So, because it will be undetermined system, especially if you use pooling operations. How do you do it? The convolution step.
Yeah. So the convolution is exactly the opposite of the convolution. If you implemented the forward pass of the deconvolution is exactly the backward pass of the convolution and the other way around. Does this answer your question?
But there is possible several values for input matrix which give the same output, isn't it? This is why this step is, this system which you solve on the backward, when you move backward in the network, will be undetermined. It will be an undetermined system, underdetermined system.
But it's exactly the same in the normal backward parse of the network then. Right? Yeah, maybe we can discuss this offline as well. Thank you.